The next example is g of s is equal to k multiply 1 minus s over b divided by s multiply 1 plus s over a. So let's see what happens in this system. What happens to the Bode diagram of this system? 20 log of g of j omega and then phase of g of j omega. So what is important? The frequencies that are important is b and a, and suppose that b is less than a, which means that we have the 0 first and then we have the pole. So suppose that b is here and a is here. And also suppose that k is something between b and a. So k is greater than b and less than a. If we want to plot the Bode diagram, so in low frequencies, the amplitude, the magnitude of these two terms is 0 because we have the 1. So the only terms that have amplitude in low frequencies is the gain and the integrator. So the integrator, due to the integrator, the slope of the magnitude would be minus 20 dB per decade. And due to the gain, it will shift this minus 20 up and down, depends on if k is positive, k is greater than 1 or less than 1. But what is important is that in one of the examples, in this example I showed you, if we have 4 over s, then the Bode diagram will cross the horizontal axis at omega equal 4. Therefore, if we have k over s, this crossover frequency would be k. So if I want to draw only the Bode diagram for k over s, and we know that k is in between b and a, let's say k is here. This is k. So I will not draw it with a solid line, just with a dashed line. This dashed line shows the frequency response, the magnitude of the Bode diagram only for k over s. So it will cross the horizontal axis at omega equal k. But what is important is that before we reach to k, the 0 happens. So because of 0, the amplitude or the magnitude of the Bode diagram, slope of the magnitude will increase by a factor of 20 dB per decade. So therefore here the magnitude is minus 20 because of the integrator, and if there wasn't any 0 here, it would cross the axis at k, but because 0 has happened here at omega equal b, it will increase the amplitude by 20 dB per decade. Therefore here it would be flat, so it would be constant. And then when we reach to the next frequency, which is a, because a is a pole, so it will decrease the amplitude again by a factor of 20 dB per decade. So here is minus 20 dB per decade, but here is 0. So in between b and a, the slope of the amplitude of Bode diagram is 0. So it's something like that. And if you want to talk about the phase, so let's see what we have for the phase. In low frequencies, because k is positive, the phase due to the k is 0. The other terms, because they have the 1 here, so the phase also is 0 for the other terms. The only term that has a phase is integrator. So phase of integrator is minus 90. So we have this minus 90 here. I can also specify B and A here. So it is minus 90, but we know that B is a 0. If it was 1 plus S over B, if it was a 0 in the left side, then the phase would increase 90. So it would increase to, it would increase. But because now B is a non-minimum phase 0, it is a 0 in the right side. So the behavior of the phase is the opposite. It will go down. So basically it will go down. If there wasn't this pole, the phase would go to minus 180, minus 19 due to the integrator, another minus 90 due to the 0 in the right side. But because we have another pole at s equal a, or omega equal a, so what happens is that the phase goes another 90 degrees further down. So it will actually go down to minus, so minus 90, and then another minus 90 for the 0 and another minus 90 for the pole, so it would be minus 270 degrees. So this is the behavior of the phase, and then we also had the behavior of the magnitude. And the next example is even more interesting. Suppose that the Bode diagram of a system is given and you are going to find the transfer function. Basically, it's the opposite with what we have been doing. And the reason that this example is interesting is that in reality, in many cases, we can apply, as I mentioned before, we can apply sine wave to a system in different frequencies, and for each frequency we can find or measure the amplitude and phase of the output, and then basically for each frequency we have one point on the Bode diagram, and when we have enough points we can draw the Bode diagram. So let's say this Bode diagram is drawn due to the information we have from a system, from the measurement of the output of the system. So now the question is, what is the transfer function of the system? What you should notice here, I will write the final result here, but the explanation is really important. So g of s, let's see what it is. What you should notice is that in low frequencies, the slope is minus 20 dB per decade. Because of that, we have one integrator. So that's the first argument we had. Because in low frequencies, the amplitude is minus 20, the slope is minus 20 dB per decade, there should be an integrator. And due to the integrator, the phase should be minus 90, and it is minus 90 here. So because of that, we say that gain, we haven't calculated gain, but we know that the sign of the gain is positive. If the gain was negative, then the phase in low frequencies wouldn't be minus 90, because a negative gain has minus 180 degrees phase, and if you add minus 180 with the minus 90 of the integrator, it would have been minus 270 or plus 90, because minus 270 and plus 90, they are exactly the same. So it would have started from another point, but because it is minus 90, therefore the gain is positive. The next point is that at s equal a1 or omega equal a1, the slope has changed from minus 20 to minus 40. Therefore, a is a pole because it is decreasing the gain of the slope of the magnitude. So we have 1 S over A. I don't write the sign here because still I don't know if this pole is a non-minimum phase or minimum phase. We don't know if it is in the left side or it is in the right side. But how to find it? If you look at the phase is decreasing when you reach to this A1. Therefore, it has a normal behavior of a pole which decreases the phase. Therefore, the sign here is plus. Then we reach to the next frequency, the important frequency, which is A2. And at A2, the magnitude, the slope of magnitude from minus 40 becomes 0. So we have increase of 40 degrees, 40 dB per decade in the slope of the Bode diagram. Therefore, we should have two zeros at this point. These two zeros could be complex or real. If we go for the real poles, it would be 1 plus S over A2. By the way, this one was A1. This one is A2 squared. So we should have 2 because the increase in the slope is plus 40 because it changes from minus 40 to 0. We should have two zeros. But as I said, it could be either two real zeros or a complex zero. And from this asymptote, we don't know which one. But if we have the exact curve, then actually it's not difficult to realize which one it is. If the exact curve is here, above the asymptote, then it means that they are real. If it is actually goes down and comes back like this undershoot, then it is complex. But for now, as I said, we assume that they are real. We have two zeros here. Okay, I shouldn't have written the sign of that because we don't know what the sign is. So I should have left the sign for the later discussion. But now I can talk about that. The phase was decreasing due to the pole here, but now you can see that the phase is increasing. So because the phase is increasing, therefore the zeros are not non-minimum phase. They are in the left-hand side because the behavior of the phase is normal. We expect to have increase of the phase when we have a zero, which is happening here. And finally, we have another something happening here at frequency is equal to A3. What is that? Basically, we are decreasing. We have the decrease in the magnitude or in the slope of magnitude from 0 to minus 20, which means that we have one pole, 1 S over A3. So we have one pole is happening here, but is it plus or minus? So if it was plus, if it was a normal pole in the left hand side, we would expect to have decrease in the phase. But actually it is not decreasing, it is increasing. Because of that, this pole is a non-minimum phase pole. It is in the right hand side. So these are the poles and zeros of the system, but what about the gain? Usually in these cases, if you want to find the gain, if like the previous example, we had the cross section of this line, if we continue this line and we have the cross section, then this value is the gain, but we don't have it, it is not given. But instead, suppose that this point is given to be plus 40 decibel. So at point 1, the magnitude, we know that it is plus 40. So what is the gain? To find that, if we assume that gain is 1, so what would be the magnitude of the Bode diagram at frequency equal 0.1? We know that if the gain is 1, therefore we have just one integrator, and the integrator, the cross over frequency of the integrator is omega equal 1, which means that at omega equal 0.1, the magnitude would be 20. if gain is 1. But the magnitude now is not 20, it is 40. So 20 of that is because of the integrator, another 20 is because of the gain. So we know that 20 logarithm of k over s or k over j omega, when omega is 0.1, it is equal to 40. So the question is, what is k? Why I have written k over j omega is basically k over s, because the other terms, the magnitude is 0, because this 0.1 is less than the frequencies of that. So when we are talking about frequencies less than the frequency of the pole or 0, the gain, the magnitude is 0. But the only terms that have magnitude is the gain here and also the integrator. Therefore 20 logarithm of k over j omega, and j omega is actually s when you substitute s equal j omega. At frequency equal 0.1, it should be 40. Therefore k over j omega, the absolute value of that, so I forgot this absolute value. Therefore k over omega should be, so logarithm of something is 2, then that one should be 100. When omega is 0.1. Therefore k is 10. Which actually it does make sense, because 20 logarithm of 10, logarithm of 10 is 1 and 20 logarithm of 10 is 20. So if the gain was 1 at omega equal 0.1, the magnitude would have been 20, but now it is 40. So this 20 increase, it should be due to the gain. And what gain gives you 20 dB increase in the magnitude? It would be actually 10, because logarithm of 10, as I mentioned, is 1 and 20 multiply logarithm of 10 is 20. So this was another example. We had the Bode diagram, and then I showed you how to write the transfer function from the given Bode diagram.